Hello, welcome to lesson 4 on our SPSS training. This is an introduction to inferential statistics. In lesson 2, we look at descriptive statistics, where we said it describes the characteristics of a data set, such as the mean, the standard deviation, the frequencies, and others. In this lesson, although we are still on our SPSS training, but we are not going to open the SPSS software, because I believe that before we can understand and interpret our results effectively in SPSS, we need to understand some key concepts in inferential statistics. So in this lesson, that is exactly what we are going to do. We are going to look at the definition of inferential statistics, the hypothesis testing. Then we will look at types of hypothesis tests, steps in hypothesis testing. Then we will solve an example manually so that we understand the whole point of inferential statistics and hypothesis testing, and you'll also be able to interpret our results very well when we use the software SPSS to analyze our data. So let's dive straight into it. What is inferential statistics? Inferential statistics refers to methods that allow you to use data from a sample to make generalizations or inferences about a population, and it helps researchers to draw conclusions and make predictions about a population using the sample data. When we look at the definition for inferential statistics here, we can see these two keywords. We can see population and we can see sample. So let's try to understand these key terms. So what is a population? A population is the entire group of people or items a researcher is interested in studying. Example, all voters in a country, all customers of a company, all students in a school, or all phones of a specific brand. So when we look at all these examples, we can see the word all. We can see the word all, meaning that every single person or item is included in the population. Let's look at a sample. A sample, on the other hand, is an unbiased subset of the population chosen to represent it. Example, 1,000 voters surveyed in a poll, 200 customers of a company, 300 students from a school. We can see that this word unbiased has been used to qualify the word subset, meaning that a smaller group that we select from the population should be unbiased. All different groups of the population should be represented, and we do that by using the appropriate sampling techniques. So I want to use this picture to explain the difference between a sample and population. So we have two circles here, or oval shapes here, and with a bigger one we can see different dots which are different colors. You can see that some of the colors have been repeated. Almost all the colors, we have multiple of them, but when we come to the sample, we see only one of each of the colors. They are colors from this bigger circle. So we can say that in this smaller circle, each one, so let's say this green color here is representing all the green in the bigger circle in the population. So that is a sample. A sample is a subset of the population. Let's continue. So why do we use a sample instead of a population? These are some of the reasons. One, mostly it is impossible or very difficult to get everyone in the population. Then two, it will be very time consuming. Three, it will require a lot of resources or money. So these are not all the reasons why. There are other reasons, but these are the major ones. And because of these reasons, what we do is we select a smaller group, that is the sample, and we aim to make it as representative or closely reflect the entire population by applying appropriate sampling techniques. So in statistics, we have different sampling techniques which are known as probability sampling techniques, and they are used to ensure that our sample is representative of the population it is describing. So let's say we are conducting a research about university students. We know that universities mostly have large populations, so we can also have a population which is very large and a population that is not too large. We know that universities have their population to be very large. So if you are conducting a research about university students, or if you are conducting a research in a university, it will be very difficult to get everyone to participate due to the reasons you've already mentioned here. So we just select a sample, but we try to make it representative as possible. So for the students, for instance, we should make sure that students from different departments are represented. We should make sure that different year groups are represented, and we should make sure that males and females are well represented in our sample. so that the results we get can speak for the entire population and not just for a portion of the students. So that is what we mean by a representative sample. Let's move on to the next thing we want to look at, which is hypothesis testing. So what's hypothesis testing? Hypothesis testing is one major aspect of inferential statistics. We cannot talk about inferential statistics without talking about hypothesis testing. So what is it? Hypothesis testing is a method to decide if a claim about a population is true or not based on sample data. It helps to decide whether there's enough evidence in a sample to support a specific claim or hypothesis. So there's a claim about a population parameter like the population mean, population proportion, or variance. So what we do is we use a sample to test whether this claim or assumption is valid or not. So if hypothesis testing is about testing a claim, what is hypothesis itself? So a hypothesis is a claim, statement, or assumption about a population parameter, example the mean, proportion, or variance, that is validated or refuted using sample data. Let's look at the key components of a hypothesis. It has two major key components, which are the null hypothesis, which is the default assumption, often states that there's no effect, no difference, or no relationship. An example, the average height of Ghanaians is 170 centimeters. In other words, the average height of Ghanaians is not different from 170 centimeters. Then the alternative hypothesis, the claim you are testing for. So here we are testing to see a difference. We want to see the average height of Ghanaians is different from 170. But mostly in our statistics and hypothesis testing, we don't write the null and alternative hypothesis in sentences or words form like this. We mostly write it this way. So the null hypothesis is written as H0, and here we have H0, which states that mu is equal to 170 centimeters. Then H1, which is sometimes written as HA, the alternative hypothesis, which here is stating that the mu or the mean is not equal to 170 centimeters. So this is a two-tailed test because the alternate hypothesis contains not equal sign. Not equal sign in the alternate hypothesis indicates that this is a two-tailed test, meaning our claim is that it can be higher or lower. So we've not stated a direction. We are not saying it is higher or lower. We are just saying that it is not equal to this. It's different from it can be lower or what it can be higher. So if the claim was that it's less than or greater than, that would be a one-tailed test. If you want me to do a video to explain this better, the two-tailed and one-tailed test better, let me know in the comment section so that I will do a video on that. That might not be part of our SPSS lesson, but also be on the channels. Now let's look at the different types of hypothesis tests that we have. We have Z-test, which is used for large samples and known population standard deviations. Then we also have T-test, used for small samples, unknown population standard deviation. And under the T-test, you have one sample T-test, which is used to compare the mean of a single group to a known value. Then we have two sample or independent sample T-test, which is used to compare the means of two different groups to see if they are significantly different from each other. And we have the paired sample T-test, used to compare the means from the same group at two different times. It is mostly called the before and after test. We also have the ANOVA or analysis of variance, which is used to compare means across three or more different groups. Then we have the chi-square test, which is used to check whether there's a relationship between qualitative variables. We also have other types of hypothesis tests. We will look at each one of these, the major ones that we've mentioned here. We will look at each one of them in subsequent lessons. Now let's look at the steps in hypothesis testing. I've broken down the steps into 5. Some people can decide to break it down into more than 5, but I've decided to break it down into 5 different steps. And these are the steps we follow when we are doing it manually, as we are going to do in this lesson. So that will be the practical aspect of this lesson. We are going to solve one example manually to get a clear understanding of the whole thing. So the first step is to state the null and alternate hypothesis. The second step is to select a level of significance. Third step, identify and calculate the test statistic. Then step 4 is to formulate a decision rule, stating when to reject and when not to reject the null hypothesis. So mostly the decision is based on the null hypothesis. And we have the final step, which is the decision or the conclusion based on our decision rule that we've already stated in step 4. So I want to say something about the level of significance. The level of significance is designated alpha. So it's also called the alpha level or the level of risk. An alpha level of 0.05, which is 5%, is mostly used. It accounts for sampling errors. Because we are using a sample to make a decision about an entire population, we cannot be certain or we cannot be 100% sure in the decision we are going to make. That is why we select this alpha level to account for the errors. So if we select an alpha level of 0.05, it means we are 95% confident. And we can be 95% confident, but we can't be 100% confident. And this is what is mostly used in most research works, 0.05 alpha level or level of significance. So let's take one example of hypothesis test, then try to solve it manually. Let's go through the steps and solve it manually. So this is the question. A school claims that the average score in math is 70. A school claims that the average score in math is 70. A new teaching method is introduced and a sample of 50 students taught using this method has a mean score of 73 with a standard deviation of 8. At the 5% significance level, is there evidence that the average score is different from 70? Okay, so this is the question, and we need to identify some things in the question which we will need in our calculation. Before that, we need to check for the kind of test that this is going to be. So a school claims that the average score in math is 70. There is a known value. This is a one sample test, but we cannot conclude that it's a one sample Z test or it's a one sample T test yet. That will be based on the sample size. If you have a large sample, we can use the Z test. So a new teaching method is introduced. A sample of 50. So the 50 here is a large sample. In statistics, 50 is a large sample. A small sample is any sample below 30. So above 30 is a large sample. So we can use the Z test. The Z test is mostly used for large sample with known standard deviation. But if it's a large sample, the population standard deviation is not known, we can still use the Z test. What are the measures that we need to do our calculation? We need the population mean, we need the sample mean, we need the standard deviation, and we need the sample size, which is 50. The level of significance too has been given to us. So you go through the steps and you solve this so that when we are using the SPSS to perform the analysis, we understand any step and we understand the conclusions, we understand the results, and we know how to present it well. So that's what we are going to do. Let's go through the steps. So the first step is stating the null and alternate hypothesis. So the null hypothesis here, we are saying the mean is equal to what? 70. The mean score in math is equal to 70. Then we have the H1, the mu is not equal to 70. And step 2, state the level of significance, which was given to us as 0.05. If it was not given, we're still going to use this one because this is the default or the standard alpha level or significance level. That is step 2. Then we go to step 3. Step 3 is about calculating the test statistic. We've already identified the test you are going to use, which is the Z test. So this is the formula for calculating our test statistic. Z is equal to x bar minus mu over s divided by root of n. So the x bar is the sample mean, then the mu is the population mean, then s sample standard deviation, then the n is the sample size. Let's see, the sample mean is 73 minus population mean 70 divided by 8 over root of 50. So we have 3 out of 1.13. Therefore, this is the test statistic. It is also called the calculated Z in this example because it's Z. We call it the calculated Z. Now, the fourth step is to formulate our decision rule. So our decision rule is that we reject H0 if the Z, which is the test statistic we've calculated here to be 2.65. We reject H0, the null hypothesis, if this calculated Z is greater than critical Z. That is when we are using the classical approach or the test statistic approach. We can also use the p-value approach, and that will be when the p-value is less than the alpha level or the significance level. I'll try as much as possible to explain this one so that you understand why it works like that. Let's proceed. Now we know the calculated Z or the test statistic, and we are saying the decision is to reject the null hypothesis if that one is greater than the critical. So now here we are saying that the critical or the Z critical for 95% confidence level for a two-tailed test is 1.96. So I'm going to show you how we came about that. So let me use the normal distribution curve to explain it. So we have the normal distribution curve here, a two-tailed test. Then in the middle we have the 0.95 or the 95% confidence level, which is here. Then because it's a two-tailed test, we have to divide the alpha or the significance level by 2. So here 0.05 divided by 2, and we have 0.025. Same here, we have 0.025. Because it's a two-tailed test, we divide the alpha into 2. Now, how did we get this 1.96? I've already put it there, but I'm going to explain to you how we got it. So this place is serving as a boundary between the acceptance region and the rejection region. So this place, which has been shaded red, and this place form the rejection regions because it's a two-tailed test. If it was one-tailed, to be at one side, but because it's two-tailed, meaning it can be test statistic can be negative or positive. So when it's positive, then we are comparing it to this one, and if it's greater than this one, we are rejecting the null hypothesis because it will fall in the rejection region. So how did we get this 1.96? What we will do is to find area to the left of this place, and we can find the area here already, but it's this one that we do not know. The area will be 0.025 plus 0.95, and what do we get? 0.025 plus 0.95, we get 0.975, and that is area to the left of this boundary, area to the left. So if that is area to the left, we can use this area to the left on a table called the Z distribution table to find the critical value, which is 1.96 that we found here. So let me show you how to do that. This is the Z distribution table. So you look inside the table and we locate 0.975, and this is what I've circled here. I've circled it here. Then we trace to the left. So to the left you have 1.9 there, and also trace it to the top. So on top of it vertically, we can also see 0.06 there, or 0.06. When we add it to the 1.9, it becomes 1.96. So that is how come we have 1.96 as the critical value for this value here, which is an area below the curve. So we can use area below the curve to find the Z value. We can also use the Z value to find the area below the curve. So here, if we were to use 1.96 to find the area to the left of it, you will pick the 1.9 here on the left, then on top you will pick the 0.06, then we trace both inside the table, then we get area to the left of 1.96, but this time we're using this one to find the critical value or the Z value. So that's how come we got the 1.96. So let's decide, and we are saying that if the calculated Z, which you got to be 2.65, is greater than the critical, we are going to reject the null hypothesis. So this means in this example we are definitely going to reject the null hypothesis because the calculated Z is greater than the critical Z. So we have the 2.65. I've indicated the 2.65 on the diagram, and we can see clearly that it falls in the rejection region. Because it's positive, we focus on the positive side here. It's greater than 1.96, so it will definitely go beyond it, and it's in the rejection region. So by using the test statistic approach, comparing it to the critical value, we reject the null hypothesis. So what is the conclusion? We can conclude that there is a difference between the sample mean and the population mean, or we can say the average score for this particular class is not actually 70. There's enough evidence that it is not 70 with the sample size, the confidence interval we chose, and with the standard deviation we got from it. We can say that the average score for the class is not actually 70. So we reject the null hypothesis, which states that it's not different from 70 or is equal to 70. In this case, we are accepting the alternate hypothesis that the mean is different from 70. So this is by using the classical approach or the test statistic approach. Now let's see how we can use the p-value approach as well. Now let's try to calculate the p-value from this and use the p-value approach if you arrive at the same decision or the same conclusion. We can use this 2.65 on the same z distribution table to find the p-value. How do we do that? We first need to find area to the left of this 2.65 on the z distribution table. So 2.65. So initially I talked about how we can use the z value to look for the area under the curve. So here you have 2.65, you have 2.6, and we look for the 0.5 on top here. So 2.6 here, 0.5 here. Then we trace both within the table. Then we get the area under the curve to the left of 2.65, which is 0.996. So 0.996 to the left of 2.65. But that is not what we want. We want this small area to the right so that we can compare it to the p-value. And the total area under the curve is 1. So we are going to subtract this 0.9960 from 1. What do we get? We get 0.004. But this is not the p-value yet because it's a two-tailed test. We divided the alpha level into 2. So this one too has been divided into 2 here, as we can see. So we have to multiply this 0.004 by 2 to get the p-value for this test. So p here is equal to 0.008 and alpha is what? 0.05. So comparing this, the p-value, the rule of thumb is that if the p-value is less than, the rule of thumb is if the p-value is less than the alpha level, we reject the null hypothesis. And here we can clearly see that the p-value is 0.008, not even up to 0.01. And it's less than the alpha level of 0.05. So we reject the null hypothesis. So the p is less than the alpha value and we reject the null hypothesis. So you can see that either we use the test statistic and the critical to compare and make the decision, or if you use the p-value, we arrive at the same conclusion. We reject the null hypothesis and we accept the alternative hypothesis. And to understand it better, what this p-value of 0.008 means is that when we subtract this one from 1, we get 0.9920, meaning you have to be 99.2% confident to be able to accept the null hypothesis, and that is not possible because we are using a sample and we have chosen a confidence level of 95%. So we can't do that. We can't use 99.2%. That is why we have to reject the null hypothesis. So the fifth step is the conclusion. We've already concluded. We reject the null hypothesis because the p-value is less than the alpha level. And we can see there's a significant difference between the sample mean and the population mean. So thank you very much for watching. If you have any question, you can put it in the comment section.